So today this is the first session of the LLM reading group. And the first session, I want to focus on the T5. So it is a unified text-to-text transfer transformer model. So directly diving into what is T5. So T5 stands for 5-letter T's, right? So text-to-text transfer transformer. And it uses the complete encoder decoder structure as proposed in the original transformer architecture. And it's pre-trained with a clean data set. This is a very big, originally this is also very big open crawled internet data sets, and it identifies ways to further clean it up to pre-train this T5 model. So this is as an example. So basically it's using like one T5 model to work with all different tasks, right? So without further having all different sets of parameters, it can basically use the same model with the same parameters, but serve different tasks such as translation or predict whether the sentence is grammarly fit or not, and detect, for example, some numbers, prediction numbers, and summarization. So why I choose T5 is actually according to recent LLM, besides the kind of the private secret ones like ChatGPT and all the others, there are many like open models, right? And actually, if you find, for example, this is the instruction evaluation, evaluating the different models on different data sets. And this is the average performance. So ChatGPT is clearly the winner, and of course it doesn't include all the other kind of private models over here, but like just put ChatGPT kind of as a benchmark. It clearly as a winner, and also it has like a lot more than 100 billion parameters. But all these other models, such as the FLAN instruction fine-tuned models and T5 models, and actually the top 10 T5 actually shows up 2 times there. And actually the model size is small, right? So it's just 11 billion or 3 billion over here, and it still can achieve a relatively good performance. So which means that actually T5 is an effective structure, and since it's smaller, we can adapt it for specialized tasks with a much lower cost comparing to the 100 billion LLM. So in the upcoming LLM, I may also want to dive into like the UL2 models and the NAMA models over here. So first, I want to briefly talk about what is the multitask transfer learning. So one of the T is transfer, right? Transfer learning. So in the classical framework of transfer learning, so you first have your input, and then you pre-train the model. So usually the pre-training step is to train the model to learn about all the general knowledge about the model, such as the grammar, the relation of the words, and how to put a reasonable sentence together. So that's the pre-training stage. And then the fine-tuning stage is to adapt the pre-trained model to different tasks. In the classical paradigm, the fine-tuning step will have basically for different tasks, you will have different models, will have different parameters optimized toward different loss functions depending on what task you are doing. So this is like a kind of a classical way to do a multitask learning. In the T5 is the key part is it's using the same parameters. Basically, it's using the same like text to text. It will transform all the different tasks into the text to text input formats, and then just train one text to text model with the same parameter, with the same loss functions that can work well for all different tasks. So that's a key difference, right? So in the fine-tuning stage, we just fine-tune one model that is going to serve for all different NLP tasks. So in the next slide, I'm just to show like how it's able to achieve that. So there will be some prerequisites over here. So because this is not it's not like a session on transformer or BERT model, like mainly the transformer model. So for the detailed descriptions about the transformer, I say you can look at my Medium blog. So ENAIX. So I have written a blog about step by step into transformer, and there you can learn about what is the attention, self-attention, major components in the transformer, etc. And in the BERT link, you can learn about the pre-training, fine-tuning for different tasks there. So these two can provide some more in-depth introductions to the transformer concepts over there. But even if you don't have any prior knowledge, I will try to make it also clear enough for you to, if you want to dive deeper, I hope that it can serve as a good starting point for you to dive deeper into the transformer and T5 model. So what is the setup for the T5 model? So the first is we need to have a pre-training data sets. So usually the pre-training datasets is an unlabeled text dataset. So just like for humans, if we want to learn to write, we need to read lots of books and articles, right? So the same applies to LLM. It can teach itself by just reading through lots of unlabeled text corpus dataset. So here, the T5 proposed a way to clean up the commonly website crawling dataset. It's pretty huge dataset originally, and also it's very noisy. So T5 proposed a way to clean it up. For example, it just takes sentences and ending with the terminal punctuation mark. And also, for example, it removes the pages with the codes, it removes duplicate sentences, and also it only pre-trained on the English sentences, basically using a language detection technique to filter out all the non-English text from the corpus. So this pre-training data set is greatly reduced from the original size to around like 750 gigabytes. And they also named this dataset called C4. So it's a kind of a cleaned web crawl dataset. And then we need to decide what are the fine-tuning tasks, since T5 is aimed at a multitask learning. So it tries to put together different NLP tasks, such as text classification, tasks. So there are like many different task classification in the GLUE. So this is a general language understanding evaluation dataset. And also there's a super GLUE dataset, which is more challenging language understanding task over there. So if the model performs well on the GLUE or super GLUE, especially super GLUE, it means that it has a very good language understanding. And also it adds in the summarization task, question answering the famous scored dataset, and also add some translation dataset. So although the pre-training dataset is in English, but the T5 adopt a multilingual tokenization, so it can still adapt to other languages, but the transformation needs to be learned through the fine-tuning stage. And then, so that's the data sets and the task, and then the input and output. So as I mentioned, the T5 use a general text-to-text format for all different tasks. So I want to give some example in the original paper. So this is their T5 original paper, and over here, so you can see how it formulates the input and output. So for example, this is just to predict whether the sentence is acceptable or not. So basically whether this sentence is grammar correct, it makes linguistic sense or not. So this is the original input and target. So the process, the input is, so you first give the task description, and then you give the input, and then your target output is acceptable. So this is one classification task. The other one is you want to predict whether the relationship between two sentences, right? So again, you transform your input. First, describe your task. So this is, I think, is a relationship between sentence 1 and sentence 2, and then your process target is whether it's entailment or not. And same over here. So you have the hypothesis, premise, and then you can change whether this hypothesis stands or not, or is a contradiction to the hypothesis. So basically, this is how it kind of transform any task into the text format. Start with the task prefix, and then you input your one sentence or two sentence or paragraph, and then your output is any output you want. It can be a word indicating the class labels. It can be also a paragraph saying if it's a question answering task. So that is the input output. And also it has a consistent training objective, which is a general is a language modeling objective, since it's using the encoder decoder structure. So the objective will be always to maximize the likelihood of the next token generation, right? So since it's a generative model. And as I showed, it has the task-specific prefix to say if it's a relationship prediction, if it's a question answering or translation, etc. But it also suffers some of the mismatch label issue. For example, if you want to classify into the 3 categories and you expect your target output to be this 3 word, but since it's like a general model, so we don't put any limitations in the output. It can be that the decoder still generate a hamburger, which is not like does not belong to any of the 3 words that you hope to get. So the T5, actually the title of the paper is to explore the limits of transfer learning with this transformer. So it has done a very comprehensive empirical survey and comparisons on the architecture's objectives, like all the different dimensions, practical dimensions of how you can train and apply a model, a transformer model over there. So I think we can go one by one and that paper is really long. So I put it into a more compressed format, and we can go one by one and to see what is the main conclusion for each of the component. So for baseline, the baseline model is actually just the encoder decoder, the original transformer model over here. So yeah, if you're not familiar with the transformer model, you can go look at that step by step into transformer block. And over here, I can just briefly talk about it. So the transformer is basically, it consists of the encoder and decoder, right? So it can have like a stack of many encoders and also a stack of many decoders. And within each encoder, you have your self-attention layer, basically to indicate which are the other relevant word. Basically, it's like to learn the contextual representation for each of the word given the context it is in. And then it has this layer normalization and also has this residual link. And after that, it gives it passes the feed forward layers, and then it has another residual link and another layer normalization. over here. And the decoder also have a similar structure with the encoder. The main difference is the self-attention is masked so that it doesn't attend to the future tokens. It can only attend to the past tokens. That is the previous tokens that is already observed. And also these it adds encoder decoder attention so that you can use the information from that is already derived from the encoders to decode the information. The rest is the same. The main change that the T5 applies to the regional transformer is that it uses a relative positional self-attention. And also it removes the layer norm bias. The second one thing is straightforward. If you use the PyTorch, there's a parameter saying like whether you or not you want to whether you want to turn on or off the bias. So some people learn that if they turn off the bias, actually the models learn better. And the relative positional encoders. So it's basically add the original formulas of the attention equations with the edge representations. So here's the output and X is the input. The original attention is actually a weighted average. So these are the weights to average the values of your input, right? So this is a transformation of value matrix. So your output is a weighted average of your input. And here it adds additional term here for the edge values. And then how can we derive the weight? It's based on the inner product between the queries and keys, right? To detect how strong the signal or how much attention that we should give to the nearby words. And also it adds additional term here for the edge, for the relationship between these two tokens. And actually it looks like it's a matrix, but actually it simplifies by just by the weights. So if the I and j minus I is the same, so basically if the tokens, the distance between two tokens are 2, they have the same weight for the keys and have the same weight for the values. Basically it's like it's a clipped between minus k to k. So it only apply the edge weight. So we have a vector for the keys, for the edges, with the relative distance from negative k to k, and also we have a vector for the edge values from negative k to k. So this k is the relative distance of the positions of the token in the sequence. And these are the learnable edge keys and edge values, and it's included in the attention calculations over there. So if you are not familiar with attention, I would again recommend you to read the step by step into transformer. There I have a more intuitive way to explain the attention mechanisms there. Oh, and that is the architecture. So then the next step is the pre-training. And for the pre-training, we need an objective. And also there are many different ways to pre-train. And in the baseline, they use the denoising objective. Basically, you just drop the 15% tokens randomly. For example, over here, you just say randomly select 15% tokens and drop it. And then this is your input, and then your target, you want to predict the dropped tokens, right? So you want to predict for inviting for the X position, you want to predict last for the Y position. And for the transformer, so this is the number of blocks, this is the hidden size, and the number of attention heads in the transformer model. So this is basically they put together a transformer that has similar size to the BERT model, and it's using multilingual vocabulary, which has 32K words, so that it can do the translation task, although it is only pre-trained on the English text corpus. The pre-training details, well, it takes a context window of 112 tokens. So this is the input length, a maximum length of paragraph it can takes in. The batch size is how many sequences you can take all at once. So 128, and this is how many tokens per batch. And the training size is like how many batches that you train the model on, right? So this is if you train this many steps, then multiply by the tokens per batch. And this is the number of tokens you will run to pre-train the model. And it's using the inverse square root learning rate schedule. Basically, like after the first k steps, and then it will gradually decay the learning rate until the pre-training is over. Okay, then we can move on. When we come to the fine-tuning stage, again, we decide the batch size, the length, and also how many steps we want to run. And it uses a constant learning rate. Okay, so here is the baseline performance. So, so these are the tasks that the T5 model picks to evaluate on, like the glue, super glue, and the translation. And this is a baseline average of that is pre-trained and then fine-tuned for all the tasks using the text-to-text input-output pairs. And this is the performance like without running any pre-training, and you see that the performance greatly dropped over there. So this is the initial baseline. They use T5 to basically like use one model, the same set of parameters to predict for all different tasks. So moving next, so that's the baseline. So that's a baseline. And next, let's move to the architecture. In terms of the architecture, a lot of it depends on what is the structure of your self-attention. So the black dots here means that the attention is on, and then the bright color means the attention is the attention is off. So for example, over here, if it's a causal attention like Y2, it will attend to X1 and X2, but not X3, X4, and X5. So it is a causal relationship. It can only attend to the previous like tokens that is already observed. And there's a slight modification with the causal with the prefix, where here you set a prefix, right? So say if you set it to 3, it means that all the prior 3 tokens can be fully observed, no matter for example, this block is full black, and then after k equals 3, then you apply the causal logics over there. So basically, the causal with the prefix is the combination of the full visible and causal. And based on that different logics, we can have like different models. So the first one is like the encoder-decoder model. The causal one, we can use the language model, mainly the GPT model, right? So it can only attend to the previous words tokens. Well, the prefix, the LLM is a prefix GPT model. So it's still a generative model, but you see the links here, right? So right now, like if you set the prefix to be K, you see here is like they can all attend to each other. And then after K, it will becomes the causal links again. So that's a different architectural variance. So they report the performance on different architectures on different objectives. So I have shown that the baseline is on the denoising objective, where you just randomly predict the randomly dropped words. You can also have a language modeling objective, which is to predict the next word, right? So just like the GPT, like you always predict the next word. They also explore like different architectures. So for the same encoder decoder, you can share the parameters between the encoder and decoder and thus reduce the parameters by half. You can also reduce the number of layers in your encoder decoder. Basically, you have a smaller model. And also you have your language model, which is a GPT model, and also a prefix GPT model. And here it shows the performance over there, and it seems like the encoder decoder is still like a very strong performance, like beating the other architectures over here. But also it's surprising to see that the shared parameter encoder decoder also have comparative nearly as well as the baseline performance, and it performs better than the prefix language model. So for any encoder decoder, or the idea about the shared parameters in the transformer, a good suggestion is to look at the Albert. So this stands for A light BERT. So basically it simplifies the number of parameters in the BERT model. And also XLNet. So it uses some shared parameters to reduce the model size, and at the same time performs nearly as well as the original bigger model. And also, if you compare like different objective, like denoising objective versus a language model predicting the next token objective, denoising objective performs better than the language model objective. Okay, when we're talking about objective, I think we can talk about what are the different variants of objective. Um, so over here, so it shows that so this is a prefix language modeling. So this is the next token prediction with some prefix objective. The BERT style is the random word. You drop random word and you predict the dropped word. Deshuffling is you just randomly shuffle the token in the sequence, right? Say if it's a sentence, you just randomly shuffle the words in the sentence, and then you try to let the transformer to recover the original sentence from the shuffled words. And from here, you can see the BERT style objective kind of wins over comparing to the other pre-training objectives. And comparing to the BERT style, like the mask language modeling, there are also different variants. So one is you just have like a 15% corruption, right? So so like 90% mask, like the 10% random tokens, and also I think you also have some like randomly replace some word with some random word. That's original BERT language modeling. And your output is original full text. So basically you're trying to recover the full original text. The mask style is like 15% corruption. And again, the 100% mask is you want to predict the full text in your output. And then you can also replace the corrupted spans. So in the literature, you can choose what is the average length of the span. Say you want to, for example, you can drop two words in a row, or you can drop 3 words in a row, right? So that is the length of the span. And then you can indicate, okay, I want on average a span length of 3. So on average, you drop the words like on average like 3 words in a row over there. And then you just replace it with some placeholder, and then you're trying to predict what is dropped word for these placeholders. And also you can just put it without any placeholders, and then you just put them in order over there instead of predicting for the full sentence. And interestingly, so they pre-train against these different variants of pre-training objective, and then they find that the short target pre-training objective wins over the full sentence recovery, and also because it's faster to train over there. So it seems like if you just use like say corrupted spans of words and just to predict the words for the tokens, it kind of wins over many different tasks. I think these two are comparative, except for superglue, the corrupted spans has a lot of wins over there. So the next is this paper also explore the pre-training data set. Yeah, so it basically like so this is the original common crawl data set with just a heuristic filtering, and then this is again the common crawl data set, the C4 data set, but use language detection to extract the English only text, and also it further filter the C4 data set to remove the non-news content from the text. So the C4 becomes a news-like data set. The fourth variant is it use the high, like the ready score, to kind of evaluate what is the quality of the web pages, right, and how useful it is. So it only keeps the high quality web pages as sorted by the community and just retain that for this web text like data set. So I think this data set is like high quality, useful content data set. Also, it pre-trains with the Wikipedia data set, and also Wikipedia plus this book corpus data set. Okay, let's see what's the performance. So this is a variance of data sets, and then this is the different task, the same task, right? So glue, super glue, translation, etc. And this is the size of the data set. And as you can see over here, although like the original C4 is like, the unfiltered C4 is a lot bigger than the C4, right? But actually the performance does not improve with the larger data set. So it actually means that cleaning the pre-training data set and how can we make the pre-training data set more relevant for the task at hand matters a lot. For example, over here, the news-like dataset means that this dataset is more news-like, right? And it achieves like the very high, like comparatively higher scores for the superglue due to I think it achieves like the highest on one of the tasks in the superglue, which is from the news domain. And also the Wikipedia plus this data, the TBC book corpus data set, it achieves the highest score in the question answering task because this question answering task is from Wikipedia. So basically the conclusion is first, we need a high quality, cleaned pre-training data sets. Will help with the improve the performance regardless like an unfiltered noisy data set actually will harm the performance even if the data set is huge. The second is if we can find the pre-trained data set that is more specific to the domain for the downstream task, it can also improve the performance on the for the fine-tuning stage. The other exploration they did is they basically either they like pre-train with a full set or they just use a subset of the original data set. So basically you see it's like they just use like 64 times of like 1/64, like a fraction of the original data set, but repeats the data set 64 times so that the training steps remains constant, so that the token observed, it remains constant, but the actual data set is like much smaller than the original data set. So they kind of just use a small fraction of the full data set, but they repeat the small data set by a lot of times. And then they want to see what is the performance over there. And of course, you can see that, of course, like pre-train with a clean full data set wins over. But also, it's very interesting to see that even if you decrease the data set size by 64 times, the performance is still kind of holds over there. So it's does not degrade much. But if you make it like 200 times like smaller data set, but you repeat more, the performance starts like degrading, start decreasing from there. Yeah, so basically it actually means that lots of repetition does not do any good. It may overfit your pre-training data sets, and it may harm the downstream task actions. So the best suggestion is just to get a full data set and as much as you can, and to make it maybe repeat a few times is okay, but as you repeat the more, the more harm it may do to the downstream task. Lastly is about the transfer approach. So this is on the efficient fine tuning, right? So without, should we always like fine tune the full model, or should we just fine tune partially, like fine tune partially of the model? We'll find other more efficient way to fine tune the model. One key idea in the efficient fine tuning is adapters, using adapters to the transformer. So this is like your original transformer. And then you can add adapter layer module right after the feed forward layer. And same here. And then you only, when at fine tuning, you only update the adapter weights. So you only update the layers in the adapter module while freezing all the originally pre-trained model weights. So the idea is like you would only require to update the weights in the adapters, which are much fewer than the original parameters in the transformer model. There's another way to fine tune is gradual unfreezing. Basically, you first unfreeze the last layer and then freeze the rest of the layers, and then fine tune that one, and then gradually unfreeze the lower layers in your fine tuning. So and also, so they report the performance, like, so all parameters, like you fine tuned on all parameters for this different task, or you use adapter layers with a different set of hidden dimensions. So basically, the higher the number, the D, the more complicated task it can learn. But also if your task is very simple, then it will become like overfitting over there. For example, in the CNN over here, right? So at 512, you get like a score of 17, almost close to 18. But if you increase the hidden dimensions in the data layers, the performance actually drop. And gradual unfreezing actually I don't think is doing any improvement, so it's not that effective for the T5 model over here. Yeah, it's very interesting to see that like when the hidden dimension is 512, it actually gets close. Yeah, but this super glue is far lower than the all parameters fine-tuned model. Yeah. While the adapters, although the fine tuning is efficient, but it will the performance may drop to compromise your computing cost there. And then last in the T5 survey, they have compared the ways to scale the model and computing up. So basically, it's like, say if we want to increase our computing power by 4 times, either by increasing the training times, like you run more epochs, run more steps, or you increase your model size, right? And then what is the performance on the downstream task? So this is your original baseline model. You can choose to run more training steps, run more epochs. You can train to increase your batch size, but still the same training steps. You can increase your model size. So 2 is still 4, right? So you basically you want to keep it like say if you just want to compute increase your compute power by 4 times. And also you can choose to ensemble it. Basically you can choose to pre-train, like independently pre-train 4 models, and then you also independently fine-tune those 4 models, and then you just learn to ensemble them together. Or you can just pre-train 1 model and then independently fine-tune them. So you end up with 4 models and then you ensemble it together. And this is the performance on all these different tasks. And over here, they conclude that actually the more, the larger the size, and also the more training steps, the longer you run, it will help with the performance, especially for the more challenging task, such as the superglue. So superglue is one of the most challenging language understanding evaluation task. So if you performs well, it basically can distinguish your strategies better. So if you see like there's a big leap over here, it means that your strategy actually can play a role to learn more complicated task over there. So basically here it tells that the larger the size, the longer you run, it can perform better for the task across. The translation is a little bit special because the key part that they haven't explored is they pre-train with the multilingual data set. Like if you not only pre-train on English but also pre-train on the other languages, the performance should improve. But here in the paper, they just show a pre-train model with English only, and then just learn to translate during the fine-tuning stage. Okay, so basically that's what the T5 is about. So they propose a baseline. They propose a framework to accommodate all the tasks into the text-to-text format. And then they propose a baseline, and then they explore the different variants of the architecture objectives, etc., etc. And then they reach their conclusion. Right? So in the end, they identify, they basically release a T5 model that is pre-trained with the span corruption objective. With the average span length of 3 means that you can drop, say, steps with batch. So this is like you can drop 3 words in a row and then you predict these 3 words. Of course, you can also drop 1 word and then you can also drop, say, 5 words. But on average, the span length you drop is 3. And also the T5 is trained with much longer training steps. And which gets it like the model is trained on 1T tokens. That is the 8 size of BERT of the original BERT model. And also it releases a different model size. So like small one, base one, X large, and the XX large is 11 billion. So this is at the time that the T5 is proposed. I think right now the T5 is trained on like much larger, can be also trained on much larger model, and also you can directly fine tune it. Although it's like 11 billion or maybe 20 billion, it's still much smaller than 130 billion like ChatGPT and other super large models. So it's if it can achieve like comparable performance, it will save lots of cost comparing to the super large ones. And also it's propose a multitask pre-training, right? So during the pre-training, at each checkpoint, it also monitors like some downstream task performance to make sure that the pre-training does not too overfit to the pre-trained datasets. And also it fine-tuning on the glue, super glue, etc. task dataset with a 8 batch size. So and this is the benchmark of the T5 models comparing to the previous literature state-of-the-art best performance for all the different tasks in the NLP. So basically it's still the glue and super glue, but here the table shows the detailed performance for each of the tasks in the glue dataset. And also super glue, it also has like lots of different tasks in the super glue dataset. And you can see the average performance over here. So the glue average is the average performance of all of this till here, I think. Yeah. And then this is the average performance. So previous batch is you fine tune, you would have like a separate model, potentially like for different tasks. You would fine tune the same pre-trained model for different tasks, but here with T5 you can have only one model for different tasks, and it still it even beats the performance for the previous batch for the glue, although the improvement is not that huge. But for the super glue, which is a more challenging data set, the improvement is a lot. So it's a big jump over here, especially if you compare it to 11 billion data set. Well, if you mention whether it's really a fair comparison, since the previous batch may not have as large as 11 billion, right? Maybe because of the gain is because of the larger model. But if you compare it to like a 3 billion model, it also like improves a lot comparing to the previous batch models. Yeah, and for the translation model, it does not have obvious gain there. It's mainly because of the pre-training is English only. So a multilingual pre-trained T5 model could have additional gains for the translation task. Yeah, so basically that's the conclusion of T5. Looking back, T5 is actually just use the original transformer, but a small change to the attention layers. Then it has done like a very exhaustive explorations of objective, training, data size, model size, and fine-tuning tricks, etc. And then they reach a conclusion. And also one contribution is to they release the C4 dataset. So it's the cleaned common crawled website datasets along with the model release, so that you can actually use that datasets for research and also for say to pre-train your own model over there. And also it released like a different model artifacts so that you can further fine-tune these artifacts to customized downstream task over there. Yeah. So that basically concludes the T5 model. Yeah, so if you look at the original paper, it's a pretty long one, but I think I have covered most of it. The original paper, you can also look at like more details into like more detailed results and more detailed like specific examples Yeah, that paper is really long, but I think if right now if you look at the T5 model paper, I think it should be easy for you to explore like different sections, components over there. Yeah, that's all I want to present. And I think I can, and we are on the clock at 3, but I think I can stay for a few more minutes if you have any questions or any comment or anything else like you want to discuss regarding transformers or LLM that you want to discuss with the community here. Thank you.